Good morning friends. Welcome to Parnika's Tutorials YouTube channel. In the last video, I have discussed what is an AVL tree, what is the need for AVL tree and what is the balancing factor. I hope you have watched that video. If you did not watch that video, I request you to go back and watch that video and come back to this video for better understanding. In this video, I want to discuss various rotations in the AVL tree. We have 4 rotations in the AVL tree, which is LL rotation, RR rotation, LR rotation, RL rotation. There L is a left, R is a right. Let me write down so that you will understand. We have 4 rotations in the AVL tree, which is LL rotation, and we have RR rotation, and then we have LR rotation, and we have RL rotation, where L represents left, R represents right. Now let me discuss about each one in detail. So I request everyone to watch the complete video for better understanding. First let me discuss about LL rotation. Okay. Now first thing, AVL tree also should satisfy the binary search tree property. What is the binary search tree property? All the elements which are there in the left subtree should be less than the root node, and all the elements which are there in the right subtree should be greater than the root node. Now let's say that I want to insert elements 10, 7, 5 in the binary search tree or in the AVL tree. Now let's take that. What is the element first you want to insert? You want to insert 10. Now after inserting each element, you need to compute the balancing factor of all the nodes in the AVL tree. Now compute the balancing factor for this one. What is the way to compute the balancing factor? Balancing factor is equal to height of the left subtree minus height of the right subtree. What is the height of the left subtree? Is 0. What is the height of the right subtree? Is 0. 0 minus 0 is 0. So, what should be the balancing factor of each node in the AVL tree? It should be in the range from minus 1 to 1. So, it is 0. So, I can say that it is satisfying the AVL tree property. Okay. Now, you need to insert 7. Now, 7 where you will insert? 7 should be left subtree of the root node, because all the elements which are there in the left subtree should be less than the 10 or the root node. Now 7 is less than 10, so you will insert towards the left side. Now after inserting 7, again you need to compute the balancing factor of all the elements or all the nodes in the AVL tree. Now compute the balancing factor of this one. Height of the left subtree is 0, height of the right subtree is 0. Now compute for this one. Height of the left subtree is 1, height of the right subtree is 0, so 1 minus 0 is 1. Still it is okay, because the range should be minus 1 to 1, so this is 0, this is 1, okay. Still it is an AVL tree. Now I need to insert 5. Where should I insert 5? 5 is less than 10, so I will go to the left subtree. 5 is less than 7, so I will insert here. Now after inserting 5, again you need to compute the balancing factor of each node. Now what is the balancing factor of this node? Height of the left subtree is 0, height of the right subtree is 0, so this will be 0. Now for this node, what is the balancing factor? Height of the left subtree is 1, height of the right subtree is 0, so 1 minus 0 is 1. Still it is okay. Compute the balancing factor of this root node. Height of the left subtree is 2, height of the right subtree is 0, so 2 minus 0 is 2. Now I can say that this is not AVL tree. Why? In an AVL tree, the balancing factor should be from minus 1 to 1, but it is here 2. So I can say that this is not AVL tree. If it is not an AVL tree, if you want to make it to an AVL tree, we need to go for the LL rotation. How I am saying it is an LL rotation? Please listen. Which is the element you have inserted? 5. Because of that one, the balancing factor of this root node became 2. So from this node, traverse to the newly inserted node. Newly inserted node is 5. From 10 you need to go. So 5 is there in the left subtree. Okay. How will you find? Because if the element is there 5, it should be there in the left subtree because it is less than the 5. So the newly inserted element is here. So to go there, first you are going to the left hand side. Am I right? Then from this one again 5 you are going to the left hand side. So that's why I am saying that it is LL rotation. Let me discuss again. If you want to find which rotation you need to follow from the root node or not from the root node, what is the node whose balancing factor is out of the range from that node? Here it is root node, but usually it may not be a root node. Okay, is it clear? So whose balancing factor is out of the range from that node, go towards the newly inserted node. So it is LL rotation. So you need to go for the LL rotation. Now how I will go for this LL rotation? Take the middle element. Okay, meaning is that this 7. Keep that 7 and rotate this one towards the right side. Okay, now if you keep this one tightly, hold it tightly and rotate this binary search tree in the right hand side, then it will be looks like this: 7, 5, 10. Now you look at, is it still satisfying the binary search tree property or not? What is the root node now? 7. 5 is less than 7, so it is there in the left subtree. 10 is greater than 7, it should be there in the right subtree. So it is satisfying the binary search tree. Now we need to look at whether it is satisfying the AVL tree property or not. How I will look at? I will compute the balancing factor of each node. Now what is the balancing factor of this node? Height of the left subtree minus height of the right subtree is 0. This one is height of the left subtree is 0, height of the right subtree is 0 because there are no elements in the left hand side and the right hand side. Okay, 0. Now what is the balancing factor of this one? Height of the left subtree is 1. Height of the right subtree is 1. 1 minus 1 is 0. So all the elements balancing factor is in the range of minus 1 to 1. So I can say that this is satisfying the AVL tree property. Which is not satisfying, we converted into AVL tree. So this one is called as LL rotation. How we have performed is that, let me discuss again. Take the middle element, hold it, means middle element means because here it is 10, 7, 5 is there. Or you can look at, or you can say like this: from this node, next node, okay, its child, you hold it tightly and you rotate towards the right side. If you rotate, it will fall to the 10 and this will be there in the left hand side. So this is your LL rotation. I request everyone to note down this one. Now let me discuss about RR rotation. Okay. Now let me discuss about RR rotation. Okay. Now you want to insert 10, it is okay. The balancing factor is 0. Again, I will not discuss. Now you want to insert 12. Okay, 12 is greater than 10, so obviously we will insert in the right subtree. Now balancing factor of this one is 0. Balancing factor of this one is minus 1 because height of the left subtree is 0. Height of the right subtree is 1. So 0 minus 1 is minus 1. Still it is okay. Okay, now you want to insert 15. So 15 is greater than 10, greater than 12. Now you will insert. After inserting 15, again you need to compute the balancing factor of each node in the AVL tree. Now you look at, what is the balancing factor of this one? Is 0 because height of the left subtree is 0, height of the right subtree is 0. What is this one? 0 minus 1 is minus 1. This is 0 minus 2 is minus 2. Now this is not in the range of the AVL tree balancing factor. What is the AVL tree balancing factor? Minus 1 to 1, but this is minus 2. So I can say that this is not AVL tree and it is a right skewed binary search tree. Now, which element you have inserted? 15. Because of 15, the balancing factor gone to minus 2. So, from this node, go towards the newly inserted node. How you are going? First you are going to the right side, then again you are going to the right side. So that's why we are calling it as RR rotation. In this RR rotation, you hold the child of the node, because this is the node is whose balancing factor is -2. Hold the child, okay, and rotate towards the left side. Now if you hold this one and rotate towards the left side, then it will be 12, and this one will fall towards the left side of the 12, and 15 will fall towards the right side, because I am holding this one tightly and I am rotating left hand side. So now look at whether it is satisfying the binary search tree property or not. 12 is the root node now. 10 is less than 12, so which is there in the left subtree. 15 is greater than 12, which is there in the right side. Now you need to compute the balancing factor of each node. 0, 0, 0. Am I right or wrong? So which is in the range of AVL tree. So I can say that this is an AVL tree. Previously it was not AVL tree. After performing the RR rotation, we got into the AVL tree. So I hope you have understood how I identified that it is RR rotation, and if I identified it need to be RR rotation, how I performed. I hope you have understood. Now let me discuss the LR rotation. Okay. Now let's take that I want to insert 10. Okay. As it is a root node, there are no more elements, so the balancing factor will be 0. So no problem. Now I need to insert, okay, I need to insert 7. Now 7 will be there here. Are you able to understand? Because 7 is less than 10, so it will be there. Now what is the balancing factor of this node? Is 0. What is the balancing factor of this node? Which will be 1 minus 0 will be 1. Okay, still it is okay. Now you need to insert 8. You want to insert the element 8. 8 is less than 10, so obviously you need to insert towards the left subtree. 8 is greater than 7, so you need to insert into the right subtree. So this is the binary search tree. Now we need to check whether it is AVL tree or not. After inserting the new element, again you need to compute the balancing factor of each node. What is the balancing factor of this node? Is 0. Height of the left subtree minus height of the right subtree. What is the balancing factor of this one? Is -1. Am I right or wrong? Left subtree is 0, right subtree is 1, so 0 minus 1 is -1. What is the balancing factor of this one? Height of the left subtree is 2, height of the right subtree is 0, so 2 minus 0 is 2. Now again this element is not having the balancing factor from the range from -1 to 1, so I can say that this is not an AVL tree. This is a binary search tree, but it is not an AVL tree. Are you able to understand? Now you need to look at what rotation you need to look at. Now what is the newly inserted element is 8. Because of this 8, this balancing factor is out of the range. Now from this node, you need to traverse to the newly inserted node. So first if you are going to the L, left hand side you are going, then from here you are going to the right hand side. So I can say that this is LR rotation. So this is the way you will compute what kind of rotation you need to follow. Lot of students will confuse in the LR rotation and RR rotation. Sorry, RL rotation. These are the two complex rotations, LR and RL. Lot of students will be very comfortable in the LL rotation and RR rotation, but lot of students will do the mistake in the LR and RL. Let me discuss this one is LR rotation. Okay. Now in the LR rotation, which is a combination of two rotations, first you need to perform RR rotation, LR. So first you need to perform RR rotation, then you need to perform LL rotation. Let me write here. First you need to perform RR rotation and then you need to perform LL rotation. Let me discuss each one. As it is a little bit complex, I request you to watch it carefully. Now look at this one. Leave it like this one side, and look at this one. Okay. Now what you will do is that 7 is there, 8 is there, because now you need to perform RR rotation. So take the dummy node here. There is a dummy node D. is a dummy node. Now RR rotation you need to follow. That's what I said. First you need to follow the RR rotation. So leave this element, consider the remaining elements 7 and 8 and insert a dummy rotation, dummy node. So now you need to follow the RR rotation. If you do the RR rotation, it will be 8 and it will be need to be rotated toward the left hand side. So you will get 7 here, you will get the dummy node here. Is it clear? Are you able to understand it or not? Now look at the, leave about the dummy element because this is what we have inserted. Now look at whether it is satisfying the binary search tree or not. Yes, 7 is less than 8, so it should be there in the left subtree. Now you got it. Now you add this element 10. Okay, and then it is L, then you need to perform LL rotation. Remove this dummy node now. Are you able to understand what I said? If it is LR rotation, first you need to perform RR rotation, then LL rotation. So that's why I left this one and I considered the remaining elements in that one 7 and 8 and I have considered dummy node to make you understand easily. So if I do the RR rotation, I got these elements and here I got the dummy node. The dummy node I have removed now and I have added this 10. Now I need to perform the LL rotation. If I perform the LL rotation, then it will be 8 because I will hold this node and I will rotate this one towards the right side. So if I rotate it, I will get 8, 7, 10. Now look at whether it is satisfying the binary search tree or not. What is the root node? 8. The 7 is less than 8, so it is there in the left subtree. Okay. 10 is greater than 8, so which is there in the right subtree. So I can say that it is satisfying the binary search tree. Now you need to check whether it is satisfying the AVL tree or not. What is the balancing factor of this node? Is 0. What is the balancing factor of this node? Is 0. What is the balancing factor of this node? Left subtree minus right subtree is 0. So I can say that it is satisfying the AVL tree also. So I hope you have understood how I have identified that it is LR rotation, and from this LR rotation, so finally leave this one. From this tree we got this one there. Is it clear? Are you able to understand how I have written the intermediate steps also. So this was not AVL tree. Now we converted into an AVL tree by following the LR rotation. Now let me discuss the last rotation, which is RL rotation. Okay, RL rotation. Now let's take that I want to insert the 10. It is okay. The balancing factor is 0, no problem. Now I want to insert 15. So 15 I will insert here because 15 is greater than root node. Now what is the balancing factor of this one? Is 0. The balancing factor of this one is -1. Still it is okay. Now you need to insert, let's take that you want to insert 13. Okay. Now where you will insert 13? 13 is greater than 10, so you will come to the right subtree. 13 is less than 15, so you will insert here. Now look at the balancing factor of each node. The balancing factor of this one is 0. The balancing factor of this one is 1 and the balancing factor of this one is -2. How I got it? Because height of the left subtree is 0 minus height of the right subtree is 0. Now height of the left subtree is 1, height of the right subtree is 0, 1 minus 0 is 1. Left subtree height is 0, right subtree height is 2, 0 minus 2 is 2. Now because you have inserted 13, the balancing factor of this 10 is out of the AVL tree, so I can say that this is not an AVL tree, but however it is a binary search tree. Is it clear? Now what kind of rotation we need to perform? How I will identify is that from this element I will traverse towards the newly inserted one. Go for it. First 10, from 10 you are going to the right hand side, so write the R. And from 15 you are going to the left side, so that's why I can call it as I need to perform RL rotation. RL rotation is nothing but first you need to perform LL rotation and then you need to perform RR rotation. Is it clear? This L you need to perform LL rotation, this R you need to perform RR rotation. Now what I will do, I will leave this 10, I will take the remaining elements which is 15 and 13. Okay. Now I need to perform LL rotation. So I will take some dummy element here. Okay. Then I will perform LL rotation. LL rotation is nothing but hold this 13 and rotate towards the right side. So if you rotate, you will get 13 here and 15 here. Okay. And you will get the dummy element here. Are you able to understand? Because you are holding this one tightly and you are rotating this one towards the right side, so it is satisfying the binary search tree. Now leave this dummy node. Okay, add the 10 is here. Now this is R, this is R. Now you need to perform RR rotation. If you perform RR rotation, what you will do, you will hold this one tightly and you will rotate this 10 towards the left hand side. If you do it, what you will get 13 here and 10 here and 15 here. Now look at whether it is a binary search tree or not. Root node is 13, 10 is less than 13, so I can say that it should be there in the left subtree. 15 is greater than 13, it should be there in the right subtree. So this is satisfying the binary search tree. Now we need to look at whether it is satisfying the properties of AVL tree or not. The balancing factor of this one is 0, balancing factor of this one is 0, balancing factor of this one is 0, because height of the left subtree minus height of the right subtree, 1 minus 1 is 0. So all the nodes, the balancing factor is in the range from -1 to 1. So I can say that this is AVL tree. So I hope you have understood how I identified this was not AVL tree. Am I right or wrong? So how we have identified that we have to perform RL rotation, and how I converted into an equivalent AVL tree by going for the LL rotation and RR rotation. So with this explanation, I hope you have understood how can I identify what kind of rotation I need to perform and how should I perform, such as LL rotation, RL rotation, RR rotation, etc. If you still have any doubts related to this concept, feel free to ask me in the comment section. I will try to clear your doubts as early as possible. In the next video, I will discuss about how to insert the elements in the AVL tree, and then we will discuss what kind of rotation we need to perform. Thank you for watching the complete video. Have a nice day.